Hi guys, you are welcome once again to the Smart Way lectures on the Science Ambassador series. This is a series of lectures we are running on all the areas in science, and today we are here with you to continue on thermochemistry. Now, in this lecture, we are going to look at the standard enthalpy of combustion. In our last lectures, we look at the standard enthalpy of formation and its relation to thermal stability. Now, today we are going to look at the standard enthalpy of combustion. Now, this is very simple. We have all burned before, we have all burned substances before, we have burned papers before, we have burned a cloth before, we have burned so many things, and we even burn our gas, in our gas cylinders for cooking. Now, this burning takes place with what? In oxygen, Whilst you are burning, there is a gas in the atmosphere that continuously supports your what? Your burning called what? Oxygen. Now you realize that the burning will take place or will continue to take place until all the substance that you started with what will finish up. In that case, there's still what? Oxygen in the atmosphere. So in this particular reactions, the oxygen that is supporting the burning is always in excess. So the use of oxygen to burn what material is what we call the combustion. So when you say standard enthalpy of combustion, it is very simple. Standard enthalpy of combustion is the amount of energy liberated, or is the energy liberated to the surrounding when 1 mole of a substance is burned in excess oxygen under standard conditions. The amount of energy liberated to the surrounding when 1 mole of a substance is burned in excess oxygen, is burned in in excess oxygen under standard conditions. Let's take an example. So let's assume that I have carbon, solid carbon. There's a solid carbon that I want to burn. So solid carbon. Now, how does it come? We've seen the graphite, the black thing in our pencil. That's how it look like. Now you burn it just by lighting it and burning it in oxygen. And when you burn it, what happens is that the carbon will be transformed towards carbon dioxide. Carbon will be transformed to carbon dioxide, which will come in the form of a gas. Now, the quantity, the energy it took to burn 1 mole of this carbon, the energy it took to burn 1 mole of this completely to form what we call the carbon dioxide is what we call the standard enthalpy of combustion. And this reaction must take place in the standard state. Now, we said that the oxygen must be in excess. Because if the oxygen is not in excess, it is only part of the carbon that will break, or only part of the carbon that will be transformed, and the solid material will still remain in reaction. And so you have to use excess oxygen in order to completely burn your 1 mole of the material. And so that is a very simple thing. And so when you want to do that, now if you want to account for this energy, it is the formula is given by this, the enthalpy change. I always tell you that the enthalpy change is the sum of the enthalpy of all the product minus the sum of enthalpy of all the reactants. So every enthalpy change, whether enthalpy of combustion, formation, or hydration, it is always the sum of the enthalpy of the product minus the sum of the enthalpy of the reactant. And so here, if you want to account for this standard enthalpy change, because we are doing it under standard conditions, it is proportional to this standard enthalpy of combustion. This sign means standard, and the C mean tells you combustion. And so to do that, what we are going to do is that we are going to add all the enthalpy of the product, and then you add all the enthalpy of the reactant, and then you do the subtraction. So quickly, let's look at that. So we have only one product here, and this one product, you take the standard enthalpy of the formation of that, the standard enthalpy of formation of that, of this one, standard enthalpy of formation of this, and then you minus it from the standard enthalpy of formation of the reactant, of the reactant. And so we are going to get the standard enthalpy of formation of of this, of the solid carbon, okay, and then plus the standard enthalpy of formation of this symbol must come because that means standard formation of what? Of oxygen, okay, of oxygen gas, okay. So that is what it is. So if you want to account for it mathematically, okay, just as we said that the amount of energy liberated to the surrounding when 1 mole of a substance is burned in excess oxygen. If in mathematics, if you want to account for it, you just have to subtract the reactant, the sum of all the energy of the reactant minus the sum of all the energy of what? The product. So you subtracted all the reactants. There are 2 reactants, and so here 1 mole of this, the formation of 1 mole, the energy that required to form 1 mole of this, energy that required to form 1 mole of that, and so you add them together, and then you take it away from the what? The energy that required to what? To form 1 mole of this, and the difference become the enthalpy change, specifically the enthalpy change of specifically for combustion, because for this one, okay, it is 1 mole of that was what was burned. So that is mathematics. That's how we can account for it. Let's give the next one. Let's burn glucose. This time let's burn glucose, okay. Now we know that for glucose is a food substance, and when you eat carbohydrate, usually the simplest form that you get is the glucose. And so here when you there is the glucose here, this is my glucose. I have this. Now if I completely burn the glucose now and I break all the carbon bonds and all the hydrogen bond, when I break all the carbon bond, okay, during the burning process, it will transform to carbon dioxide, okay, as a gas, and then we are also going to get water. Also water that will also come out in the form of a vapor as a gas. Now the amount of energy that it will take to break 1 mole, one mole of this glucose, okay. So this is glucose. The amount of energy required to break 1 mole of glucose, okay, completely, in excess oxygen, okay, is what we call that. So please, it must be completely. That's why we are saying that the oxygen must always be in excess in order to complete the what? The burning. So if you try to balance this equation, okay, every chemical equation must be balanced. So if you try to balance the equation, you balance carbon first. Here carbon here is 6, and the reactant side carbon here is 6, and then the product side carbon here is only 1. The number down there is 1. So you put the 6 here. Have you gotten that? Very good. And then so you put the 6 here. Okay. Then here hydrogen is 12, and in the product side, hydrogen here is only what? 2. So hydrogen here is only 2. Okay, hydrogen here is only 2. And since here is 12 and here is what? 2, I'll need to multiply by something that will get the 12, which become what? Also 6. Have you gotten that? Which become also 6. And then the last, I'll balance the what? The oxygen. I'll balance oxygen. Now I can see that here the last oxygen is balanced from the product side. So here I have 2 times what? 6 times 2. There's 2 under this oxygen, but there's 6 in front. So I multiply this what? 6 times 2, which I'll get what? 12. So I have 12 oxygen here, and then here too I have 6 times what? 1. Okay, there's 1 oxygen there. So 6 in front will affect this one, become 1. So we are going to get 18, right? We are going to get 18 oxygen on this side in overall, 18 oxygens, okay, overall. But here I have 6 over here already, so I just need 12. So how do I get the 12? By multiplying 6 here, okay, I'll get the 12, and I already add it to what? And I'll add it to the 6 to become what? 18. So 18 both sides is correct. So next one is to now write a relationship. Okay, let's write a relationship. Okay, let's write a relationship between it. Now to write it, we always have to use this. The enthalpy change for the reaction again is, I said that irrespective of what type of enthalpy, it is always the sum of what? The enthalpy change of all the product. Okay, and then you take the sum of all the enthalpy change for the reactant away from the product. Okay, so that's for all reactants away from what? All product. So because we are studying what? Because this time the standard enthalpy change, for this one is combustion, you equate this one to the standard enthalpy of what? Of combustion. The standard means that I have to put the 0 here, and C here. C tells me it's combustion. And so therefore I have to subtract all product. Okay, I have to subtract all reactants from all product. So this is my product. I write all the product here. And so when you are writing the product, you should write it in terms of formations. Okay, formations. So the enthalpy chain for the formation of the carbon dioxide. Okay, the enthalpy chain for formation of carbon dioxide, which is 6 moles of carbon dioxide. It's very important to write the 6 moles because enthalpy is proportional to what amount of substance in a reaction. And then this another reactant. So I will do that. For that. Okay, that is also 6 moles of that. It's very important that I write the 6 moles and I write the state of it. Now I have my product all added up. Now let me subtract the reactant away from the product. Okay, so this is the reactant. I also have 2 reactants here. So I have the enthalpy chain for the formation of the 1 mole of glucose. Okay, and then I will add it to, there are 2 reactants here, so I also add it to what the standard enthalpy chain for the formation of standard enthalpy chain for formation of oxygen gas. Okay, I add it to that one. So when you subtract the standard enthalpy chain for the formation of all reactants, that is this glucose and this oxygen, away from the product, which is this one, the energy change is the amount of energy that will be liberated to the surrounding. Okay, whilst we are burning the 1 mole of the glucose. Okay, in excess oxygen. So that has become the standard enthalpy of combustion. So that's how to do that. The last point is that the numbers in front must also be multiplied times the figures. They will give you a figure. You have to make sure that the numbers are multiplied. You have to multiply the numbers by the figure, and you always get your final answer. Okay, it's a very simple thing to do. Now, so therefore, if that is the case, okay, how do we practically measure the standard enthalpy of combustion? How do we measure this? How do I measure this? How do I measure it? Maybe let me take you through this one. For example, like alcohol. Okay, let me take you through alcohol. Now, let me give a last one, and then I will use the alcohol here. Okay, in this experiment. So let's quickly look at the alcohol. Here, alcohol is written as this is. I'm burning 1 mole of alcohol, so I'm going to get C2H5O C2H5, okay, and I have this. Now this is 1 mole. Now if I burn alcohol, if I burn the alcohol, okay, in excess oxygen, that is, I'm going to break all the carbons away from the hydrogen, and I'm going to break all the carbons away from the hydrogen. So hydrogen will also separate from the carbon, and they will transform to give me carbon dioxide and water. They will all come out in the form of a gas. That's why I'm writing that. So this is alcohol. This alcohol that I have broken, I have burned, and you can demonstrate it. The pure alcohol, we burn it. When you burn it, it will light. Okay, the pure alcohol, not the alcohol that has been diluted with water. Okay, so when you burn it, the alcohol will come out. The amount of energy required to burn 1 mole of the alcohol in excess oxygen is what we call the standard enthalpy of combustion under standard conditions. Okay, no, so how do we practically measure this? Let me quickly balance it before. So here should be 2. Okay, and here oxygen is 6 overall, 5 plus 1, so 6, and here is only 2, so I have to multiply here by 3, and then here oxygen becomes 4, 2 plus 2 times 2, that is 4, plus 2 times 2 is 4, that is 2 in front here, multiply these 2 here to become 4 oxygens, and then 3 here, multiply only 1 down there, become 3, so become 7. So therefore I have only 1 over here. Okay, I have 1, and I need 7 overall over here. So if I have 1, I need 7 overall here. I'll just need 6, and I'll add it to this one. And to get 6, I'll just multiply it by 6 over 2. Okay, in mathematics it means that this 6 over 2, okay, will go and multiply this 2, and this will cancel this, and so therefore I have only 6 oxygens here, which will add to the 1 to become 7. So the 4 plus 3 is 7 here, and here is also that. That is why I did that. So therefore, if you need just that for combustion reaction, you normally use fraction so that it becomes simple for us. Okay, if you need 6, you just put 6 over 2 right. Now let me give you the mathematical formula for it so that we quickly go on. So let me give you the mathematical formula for it. Here we are going to get the enthalpy change to be equal to the standard enthalpy of combustion, and here we are going to get the standard enthalpy of combustion of 1 mole of this. Okay, standard enthalpy of combustion 1 mole of this. And so here let me write the standard enthalpy of combustion of 1 mole of the alcohol. Okay, of 1 mole of the alcohol, that is the amount of energy liberated to the surrounding, okay, whilst burning its excess oxygen. That is proportional to the sum of all the enthalpy of what? Of the product. Okay, that is the sum of all the enthalpy of the reactant away from the sum of all the enthalpy from the product. So here, how many products we have? We have what? 2 products, and so we are going to get the standard enthalpy of formation of the 2 products, which is 2, okay, times the carbon dioxide, and then plus the standard enthalpy of what? Formation of, please, this symbol, look at this symbol. That there is that standard enthalpy of formation of what? 3 what? Moles of water. 3 moles of water. Okay, and then that is for the reactant side, that's for the product side, and then I'll take the what? That's for the product side. So I'll take the reactant away from the what? From the product. So I have 1 mole of this, the standard enthalpy of I have the standard enthalpy of combustion. Standard enthalpy of what? That's the standard enthalpy of formation of this. You don't combustion. We are finding combustion, so you can't use combustion here. So standard enthalpy of what? Formation of the alcohol. Okay, of the formation of alcohol. That is 1 mole of the alcohol. 1 mole of the alcohol. Okay, and then you then do that. And then plus what? The standard enthalpy of formation of what? The standard enthalpy of formation of the oxygen. Okay, that's of oxygen. So how many moles of oxygen here do we have? We have what? 6 over 2 moles of oxygen gas. These numbers must be multiplied times the value that will be given to you. So mathematically, that is the relationship between the standard enthalpy of combustion and then the standard enthalpy of formation. You subtract the formations reactions from you subtract the formations of both the reactant and the product in order to get the combustion. That is, if the reaction is combustion, that's what you do. If the reaction is combustion, that is what we are going to do. Okay, you subtract the formations, okay, from the product of the reactant away from the product in order to get the combustion. Only if the reaction is what? A combustion reaction. So basically, that is what it is. Now, in our next lecture, we are going to look at the practical determination of standard enthalpy of combustion. How do we practically measure it with what instrument? Okay, how do I quantify the energy that is given out when I burn 1 mole of glucose? So here, for instance, we have 1 mole of glucose, and we have 1 mole of ethanol that I want to burn. Now, after completely burning this one, what amount of energy, okay, will it liberate? What quantity of energy will it liberate, and how do we calculate for it? And here too is also another example, which is this one is what's called the bomb calorimeter. In our next video, we are going to bomb what? A glucose. We are going to bomb it, and then you absorb the energy, and then you calculate the energy from the reaction. So keep on watching the videos and enjoy our lectures. Thank you.